mesh. And here I will go with some refinement. So you can see that my geometry is a mesh. So meshing part is done on each where these lines coincide. This is a node. So on all of these nodes, that when you discretize the new equations on all these nodes, that equation will get solved, which is this, and this is a condensed form of one dimensional steady energy equation, or what you can also call it a heat equation, which will get solved at each node. So, and you can also do one thing like a create named selection. I will tell you it will be uh, like here I have to give one boundary condition and here I have to give another boundary condition. So if you will create name selection, it will be easy to give boundary condition in fluent. Like I will this short h1. Okay, so all of my name selection is done, like short h1, short h2. These are both long edge, and this is the surface. There will be no backside as it is a 2D problem. So backside surface will not be included in a 2D problem. So uh, like if you select, if you can see my screen, that this is for selecting corner. If you have to like create name selection or select this is for selecting corner point or something. It is a complex geometry. This is for the points. If you have to give some point load like point heat generation, or this is for selection of edge. So it will select only edge, not surface. This is selection for surface. So it will not select edge, it will only select surface. And this is for selection of whole geometry. Like it is a 2D, so my whole geometry is also a surface. So it will look like, but in 3D you can notice that if there is a cylindrical 3D pipe, then when you click on it, it will select the whole pipe, not just the surface. As it is a 2D problem, so the geometry is only 2D, so it will select both function will do the same thing. So meshing is done. Here you can look, as you can see, there are 793 nodes and 720. Each square is an element. So there are 720 elements and 793 nodes. Each of this point intersection is a node. So I can close this and 1 second. Yes. Now we are going to Fluent, where we will set up our boundary conditions and select material. So as you can see, my mesh geometry, this is mesh geometry is automatically imported, and you can see uh, my geometry part modeling is done and meshing part is done. So there are two ticks. Now I have to set up my problem. Mm, First, you have to select the scale which you have created the mesh. So I will select as I have when modeling. I have selected Yeah, mesh was created in and you can select view length in meter or I'm selecting right now, but you can select meter also. It will make no difference. Just it will show results in that only. I select meter. Okay. Now, as it is a steady, so state we have to solve. You will select steady state, and in 2D space you will select planar, and you can use this default pressure based solver, which is not of make a difference because as it is not a fluid flow problem. Now, one thing I want to change here, the unit of temperature, because I like to see in centigrade, not Kelvin, because we are much more used to centigrade unit in our study. So here from general, this will all, like I've told you, will come in general tab. Now, if you second will come in model. So as it is a solid only, so we don't have to solve flow equations. We only have to on the energy equation. So we have to click on take the energy equation, and we don't have to bother with all this because we are not solving any flow problems or like that. And here you have to add the material like so default like in fluid air is the default material and aluminum in solid. You can like add more new material like from the database of fluent database. Like this is all the solid materials. You can get copper, all. No, sorry, this is fluid, solid material. Like you will get titanium, steel, nickel, gold, copper. So you have to, but we are now just taking the default aluminum. So in cell zone conditions, as this surface is a solid, so we have to change. It is showing in fluid. So we have to make this surface solid. So you have to right click, like you have right click, you can change the type fluid or solid. I have changed to solid. Now it will automatically ask which material is this. So it will show all the material name here which you have added, but I have to use only aluminum. You can use, like you have added copper or titanium, steel, like you have a complex geometry, and some parts are made of aluminum, some parts are made of copper, so you can add that here and select different parts of geometry with different material, and different properties will get attached to that part, different thermal properties. So here apply, we so and close. So now I have selected the material. Now we come to the boundary conditions. So as I have all the named selection which I have used will come here. So the short edge is this one. So as in the problem you can see the temperature is given 500. I think it's in centigrade only. So here I will, this left edge I will assign it um, temperature. Yeah, so this is a Dirichlet boundary condition. So temperature uh, which is 500 centigrade. Then click on apply and close. On this second edge which is here, it is given 100 Kelvin, 100 centigrade. Sorry. So it is also a Dirichlet. So you will assign 100. As there is no convection, so you will assign, like in this equation, like I have said that it is not a 1D problem. 1D problem has to be solved in 2D problem. So these long edges, as there is no convection here, like in other problems, there will be heat generation and this. So right now there is no, so I have to, this part is insulated, so I will give a heat flux of 0. Now all the boundary conditions are set. You can use any method as a that flow equation is not there. We don't have to solve, so you don't have to bother with that. You just go for initialization, initialize the problem. You can go for hybrid, and then run the problem. So number of iterations, like it will take some iterations to converge the problem. So you can give first 100, or like 500, or if the convergence criteria is reached, like mm, in when you go to solution, there is residuals. So for we don't need continuity equation. We are only solving the energy equation. So this is the criteria for the energy equation. The error is 1 into 10 to the power of -6. So if this criteria is met, so our iterations will stop. So you can give like 500 or 1000 or 100, whatever. I don't know. Like it will take less iterations only, I think. So let's click on calculate. Uh, so as you can see, the solution is converged only in 5 iterations. Energy equations is converged, and the graph is below 1 into 10 to the power of -6. You can change the criteria there, but this is default selected by ansys, which is a good um, low tolerance, which for default, like simple problems. In complex problems, you have when you become expert, you can change according to the nature of the problem. So here also you can see some like contours, like temperature. So as there is no velocity density because there is no fluid involved, we can only see temperature. So so here it's 1.00 E. Here E means 10, 10 to the power of 2. So here, like you see the blue part. So here it is 10 to the power of 2, it will become 100. I don't know why ANSYS shows like this, but it always shows like this only. So here 140, you can see the colored graph here, like it is 500, which is at the left edge, which is according to your problem. And see, you can, this is the temperature distribution. Now we can also see our results in a post processor, which is built only for viewing the results. So we'll close this. So here you can see setup, and our solution is done. Tick mark, and then we can go to results. So this is our geometry. We can, like we can create a contour of the temperature. Click on contour and then select all domains, or and you have to select the temperature, and you can give like you can give global range. I will like if there will be a different problem, then I can tell you what is difference between global and local range, but as a simple problem it will not matter. And here you can select the number of contours, let's say 100, and then click on apply. Sorry. uh, so here you can see the temperature, which is 500, and it is decreasing to 100 degrees. So you get the temperature distribution on that fin for that problem. Now sir, sir,
Yes,
sir is
Samad.
there, or
Yes, Samad.
yes sir, for plotting the graph, like to take the x-axis, sir, I have to see one thing. I'm sir to
Okay, you leave it, no problem. From there, they can explore. They can explore how to plot the temperature variation
sir,
with the
chart
x-axis.
for
Now you switch to next tutorial problem. You change the boundary conditions as per the second
here.
assignment, and
Yeah, okay sir, I can explain after exploring some. It will take some time. Okay sir.
yeah, no problem. Maybe next time when we will invite you, you can clear that thing.
Okay.
For the time being, this is fine. The temperature profile has been generated. Now anyone can do post processing and plot the graph
Yeah.
whatever they want from.
And you can
Now
also
you
get
switch to
tabular values in the table, and then you can compare with your code. You can import that values in your MATLAB or with software. Then you can plot both graphs and see the difference and check your code. So in our next problem,